Welcome to part 1 of this video playlist about the preparation of phenethylamines. I've sorted the material into 3 videos according to the bond being formed, highlighted in green. In this first video we'll have a look at why phenethylamines are important compounds. Then I'll give you specific examples of the preparation by aminomethylation of benzaldehydes, ketones, benzoic acids and other benzylic electrophiles or nucleophiles. Part 2 of this playlist deals with aminoethylations of arenes or aryl halides, and the third video is about CN bond forming strategies. Neurotransmitters are mostly amino acid derived small molecules released by neurons and other cells to communicate with each other. Many neurotransmitters are phenethylamines, as those shown here. Synthetic analogues of these compounds can activate or block their receptors and are used for treating various diseases. The biosynthesis of many neurotransmitters starts by decarboxylation of an amino acid. Serotonin, tryptamine and melatonin, for instance, are biochemically derived from tryptophan. Plants and fungi also produce phenethylamines to protect themselves from herbivores. These alkaloids often bind to the receptors of neurotransmitters and can thereby induce a feeling of discomfort or nausea and a conditioned taste aversion, that is, a strong dislike for the taste or even the smell of the plant. Higher doses of these compounds are usually deadly. So, why are most natural poisons amines? There are of course exceptions, for instance the lipophilic alcohol cicutoxin or fluoroacetic acid, an inhibitor of the citric acid cycle. But many natural poisons, in particular those meant for oral delivery, are amines. The reason is that cell membranes have a net negative surface charge and act as cation exchange resins. Cations can move freely between cells and diffuse into any tissue, while anionic molecules are far less mobile. In order to be orally available, compounds must at least be slightly soluble in water and devoid of positive or negative charge. At physiological pH, amines are either neutral or positively charged, and lipophilic amines are therefore orally available. Protonated amines quickly diffuse through tissue and reach most organs, including the brain. This removes amines from the bloodstream and slows down their metabolic degradation by the liver. Thus, the body of mammals can be viewed as a loop reactor filled with a cation exchange resin, that is, an insoluble, negatively charged polymer. Ammonium salts and other cations diffuse effectively into this polymer, while anions remain concentrated in the bloodstream. Therefore, because of their ability to be neutral or cationic, amines tend to have better oral bioavailability, good tissue distribution, and a longer plasma half-life than neutral or acidic compounds. Those humans who enjoyed eating alkaloid-containing plants procreated less efficiently than those who did not like to eat these plants, what explains the bitter taste of most amines. Many natural alkaloids are also emetics, causing us to vomit. If you watch this to find out how to make mescaline, this compound is not addictive at all, because of its strong emetic effect and bad taste. As intended by the cactus which produces mescaline, most people find the experience unpleasant and not worth a second trial. The pharmacokinetic properties of drugs can sometimes be improved by converting neutral compounds into amines. When an amine-containing side chain was attached to the calcium channel blocker felodipine, a compound with a longer plasma half-life, a higher oral bioavailability, and a larger volume of distribution resulted. The latter refers to the hypothetical volume into which a given dose of drug would have to be diluted to attain the observed plasma concentration. The larger the volume of distribution, the lower the plasma concentration and the rate of metabolic degradation by the liver. Another example is the muscle relaxant dantrolene. The structurally related amine acimilide, an antiarrhythmic, has a much longer plasma half-life, improved oral bioavailability and a much larger volume of distribution. Now, back to synthetic chemistry. The most common strategy for preparing phenethylamines is by aminomethylation of benzylic electrophiles or nucleophiles. This includes condensations of benzaldehydes, aryl ketones or benzoic acid derivatives with nitroalkanes, cyanide, azomethine ylides or ammonium ylides. Benzylic halides, sulfonates or ammonium salts are also suitable electrophiles. Alternatively, benzylic nucleophiles can be added to imines or iminium salts. Benzaldehydes and aryl ketones are usually converted into phenethylamines by condensation with nitromethane followed by reduction, for instance with lithium aluminum hydride. Cyanohydrin formation and reduction is another common strategy. Less flexible is the addition of azomethine ylides to benzaldehydes, but I'll also show you some of these. Many examples have been reported of the condensation of benzaldehydes with activated amino acid derivatives such as azlactones for the preparation of phenylalanines. Enantioselective hydrogenation of the intermediate aminocinamates was one of the first examples of enantioselective catalysis. Phenylalanines cannot be readily decarboxylated, however. Benzaldehydes can also be transformed into imines and then dimerized by metals. Benzylation of nitroalkanes yields nitroketones, which can be reduced to phenethylamines, amino alcohols or aminoketones. The benzylation is tricky and only gives reasonable yields with soft benzylating reagents such as phenyl esters, imidazolides or acyl cyanides. With benzoyl chlorides, acylation occurs at oxygen and hydrolysis yields unchanged nitroalkane and the benzoic acid. Phenethylamines can also be prepared from benzyl halides, for instance by treatment with cyanide and reduction of the nitrile, or by benzylation of activated amines or nitroalkanes. Few successful examples of this last strategy have been reported because nitroalkanes are mostly benzylated at oxygen. With the aid of copper catalysts, however, it is possible to benzylate nitroalkanes at carbon. Phenethylamines with benzylic hydrogen show limited thermal stability and may yield styrenes upon strong heating, as shown here. Elimination can also become a problem during the alkylation of amines with phenetyl halides, as discussed in the third video of this playlist. Electron-deficient arenes will undergo elimination more readily than electron-rich arenes. Okay, let's start with some specific examples. This here is the most common strategy for the laboratory conversion of benzaldehydes into phenethylamines. Condensation with nitromethane usually proceeds in a high yield, and the nitrostyrene intermediates are often crystalline and easy to purify by recrystallization. Reduction of the double bond and the nitro group with lithium aluminum hydride then gives the target amine. Yields of this reduction are often lower, typically 60%, because of the many intermediates and potential side reactions. High dilution, as in this example, slows down intermolecular condensations of these intermediates and may improve the yield. A newer reduction method is treatment with an excess of sodium borohydride and a catalytic amount of copper chloride. Catalytic hydrogenation can also be successful, but may require careful optimization. Treatment of benzaldehydes with nitromethane under milder conditions yields nitroalcohols in the so-called Henry reaction. Many stereoselective variations of this reaction have been reported, as for instance this one. These alcohols can be reduced either to amino alcohols or to phenethylamines. In this example, catalytic hydrogenation mostly yielded the amino alcohol without benzylic CO bond hydrogenolysis. This is another example of nitro group reduction by palladium catalyzed hydrogenation. No epimerization of the nitroalkane occurred. Carboxylic esters do not usually react with amines at room temperature, but the formation of 5-membered lactams, as in this example, is much faster than intermolecular acylations. Alternatively, amino alcohols can also be obtained by treating nitro alcohols with zinc and acids. Again, no epimerization occurred in this instance. Here, catalytic hydrogenation would have been difficult because of the potential carbon-bromine bond cleavage and catalyst poisoning by the thioether. Also, amino alcohols or diamines do occasionally form strong bonds to the active sites of heterogeneous catalysts and act as catalyst poisons. Mixtures of benzaldehydes, amines and nitromethane can yield 2 aminonitroethanes, as in this example. These products are as unstable as Mannich products and may decompose into the starting materials upon heating or treatment with acids or bases. Their reduction to primary amines therefore requires some optimization. The stability of these compounds increases by acylation, sulfonylation or phosphorylation of the benzylic amino group. Here, a phosphorylated nitroamine was reduced with zinc and indium under acidic conditions, without CC bond cleavage. In this example, the reduction of the nitro group succeeded by catalytic hydrogenation in methanol. Here, a nitroalkane was prepared enantioselectively by treating a protected benzaldehyde with nitromethane and 20% of a chiral amine. Reduction with zinc and hydrochloric acid gave the target primary amine. Another approach to phenethylamines is reduction of benzoyl cyanides. Although this seems attractive at first glance, this route has only rarely been used. The reasons are that both the preparation of benzoyl cyanides and their reduction are difficult. This here is an example of the preparation of a distillable benzoyl cyanide. The benzoic anhydride was heated with 1 equivalent of sodium cyanide without any solvent, and the product was distilled directly from the reaction mixture. For less volatile benzoyl cyanides, the strategy shown here is more convenient. Potassium hexacyanoferrate was a source of cyanide in this case, and reaction with the benzoyl chloride already proceeded at room temperature. Other similar procedures use copper cyanide instead of hexacyanoferrate. Benzoyl cyanides are electrophilic acylating reagents that will react with water, alcohols, amines, and other nucleophiles. Thus, during their reduction, benzylation of the newly formed amine by unreacted benzoyl cyanide can occur. This can be prevented by the addition of acids or acylating reagents. In this example, benzoyl cyanide was reduced to aminoacetophenone with stannous chloride and hydrogen chloride under anhydrous conditions. Catalytic hydrogenation is difficult because cyanide can poison the catalyst. Further, hydrogenations often yield amino alcohols or pyrazines. Here, a fair yield of acetylated aminoketone was obtained by catalytic hydrogenation in a mixture of acetic acid and acetic anhydride. The enantioselective reduction of benzoyl cyanides with alpene borane has also been reported. This strategy yielded amino alcohols in moderate enantiomeric excess. Alpha-nitroacetophenones can be prepared by benzoylation of nitroalkanes. Benzoyl halides or anhydrides are not usually used because these preferentially acylate the nitro group at oxygen. Better suited are soft benzoylating reagents, such as acyl cyanides, phenyl esters or imidazolides. In this example, benzoyl cyanide was treated with nitromethane and sodium carbonate in pyridine, and the expected nitroketone was obtained in 73% yield. Few examples of such acylations have been reported. These reactions require careful optimization, also of the workup. The products are strong carbon acids and may undergo CC bond cleavage when treated with nucleophiles. Aromatic nitroketones can be reduced to aminoketones, amino alcohols, or phenethylamines. In the third video of this playlist, you can find some examples of such reductions. Here, a nitroketone was prepared from a phenylbenzoate and nitromethane with the aid of potassium terzbutoxide in DMSO. As we'll see at the end of this video when discussing side reactions, nitromethane can dimerize or otherwise decompose when treated with strong bases, especially in DMSO. Therefore, the order in which reagents are mixed and the addition rates can be critical for the success of these reactions. This example is similar to the previous one. Sodium hydride in DMF and a large excess of nitromethane was used. No fluoride displacement occurred. Strong bases can cause the violent decomposition of both DMF and DMSO, and reactions like this or the previous one should only be run on a small scale. Alternatively, a safer solvent could be tested, for instance dimethylacetamide. Instead of phenyl esters, benzoyl triazoles or imidazolides can also be used to acylate nitromethane, as in this example. The reaction was again conducted in DMSO with an excess of potassium terzbutoxide as base. Under optimized conditions, even benzonitriles can acylate nitroalkanes. In this example, a mixture of DBU, cesium carbonate and copper iodide in pure nitromethane gave a fair yield of the expected addition product. Benzyl halides usually alkylate nitroalkanes at oxygen. I'll show you an example of this reaction at the end of this video. With the aid of a copper catalyst, it is however possible to benzylate deprotonated nitroalkanes at carbon, as shown here. Even 1-nitropropane and nitromethane could be benzylated this way in high yield. Phenethylamines can also be prepared by reduction of nitriles. Under acidic conditions, hydrogen cyanide readily adds to benzaldehydes or aromatic ketones, and the resulting cyanohydrins can be reduced to amino alcohols or the deoxygenated amines. In this example, acylated cyanohydrin was prepared with trimethylsilyl cyanide. Reduction to the amino alcohol succeeded with lithium aluminum hydride. Catalytic hydrogenation of cyanohydrins can cause hydrogenolysis of the benzylic CO bond, as in this example. These reactions often require extensive optimization because the intermediate imines may undergo hydrolysis or oligomerization. If hydrogenations are conducted under alkaline conditions, a large excess of ammonia may help to prevent the formation of secondary amines. Another problem is poisoning of the catalyst by cyanide anions. Cyanohydrins can also be reduced with borane, as shown here. Borane was generated by adding trifluoroacetic acid to sodium borohydride. Here the starting material was not a cyanohydrin but a simple benzylic nitrile. Hydrogenation with Raney-nickel in acetic acid yielded the expected amine. Raney-nickel is usually used under alkaline conditions, but in this instance better results were obtained with acids. Nitriles can also be first converted into amidines and then reduced to amines with sodium borohydride. Amines do not readily add to nitriles, and here a slight excess of copper chloride was required to bring about amidine formation. Aminonitriles, like the starting material on this slide, are obtained by addition of hydrogen cyanide to imines. These products are as unstable as Mannich products and readily fragment into the starting materials. Thus, reduction to diamines can be challenging. Here, reduction with lithium aluminum hydride caused extensive decyanation. Catalytic hydrogenation wasn't successful either, and again, mostly fragmentation products resulted. Besides nitroalkanes and cyanide, various reagents with alpha-methylated amine substructure have been used to prepare phenethylamines. In this example, a lithiated carbamate was generated from a chloromethyl carbamate and metallic lithium. Addition to acetophenone yielded a protected amino alcohol. Here, a carbanion was generated and trapped with benzaldehyde by adding fluoride to a protected aminomethylsilane. A high yield of the expected amino alcohol resulted. Azomethine ylides can be generated in a number of ways. Here, treatment of trimethylamine oxide with a large excess of LDA at low temperature produced an intermediate which added cleanly to acylated imine. Hydrolysis and removal of formaldehyde with an excess of hydroxylamine then yielded a diamine. In this example, the same azomethine ylide as in the previous example was generated by heating an oxazolidine. The ylide aminomethylated diphenylacetonitrile in high yield, probably by the mechanism sketched here. The 1,2 migration of alkyl groups in ammonium ylides is called Stevens rearrangement. In this instance, the benzyl group migrated and a 2-benzyl piperidine was obtained. One potential side reaction was Sommelet-Hauser rearrangement, that is, the addition of the carb anion to the arene. But this did not happen here. This here is a more sophisticated example of ammonium ylide rearrangement. A huge excess of base and 10% of a palladium-carbene complex were required. There are certainly less wasteful and more convenient methods to prepare this product. Phenylalanines can be synthesized by condensing azlactones with benzaldehydes and then reducing the intermediate cinnamates. Azlactones are formed when N-acyl amino acids are heated with acetic anhydride, as shown here. The cinnamates can be hydrogenated or reduced chemically, as in this example. When sarcosine was heated with an excess of benzaldehyde to 170 degrees Celsius, a low yield of a decarboxylated N-methyloxazolidine resulted. This intermediate could then be hydrolyzed to an amino alcohol. Chemical decarboxylations of alpha amino acids are rare, but can be catalyzed by pyridoxal or other aldehydes. Racemic azlactones can be benzylated enantioselectively. A benzyl phosphate was the electrophile here, and the alkylation proceeded under mild conditions, with just a slight excess of triethylamine as base. Benzylic nucleophiles can be transformed into phenethylamines by addition to imines. Here, for instance, benzyl magnesium chloride cleanly reacted with a benzaldehyde-derived imine. The main problem with this strategy is that during its preparation, the Grignard reagent can be benzylated by unreacted benzyl chloride. This would yield 1,2-diphenylethane as a byproduct. This side reaction becomes faster with more reactive benzyl halides, for instance benzyl bromides or electron-rich benzylic chlorides. Imines also undergo reductive dimerization, as in the pinacol coupling. In the case here, the initially formed benzylic diamine could be epimerized with an excess of lithium to mostly one of the two possible diastereomers. Benzaldehyde-derived imines can also be transformed into acyridines by reaction with diazoesters. Acid-catalyzed solvolysis yielded an acylated amino alcohol, suitable as intermediate for the preparation of the antibiotic chloramphenicol. 2 or 4 nitrotoluenes are acidic and can be acylated at carbon. Reductive amination of the resulting ketones or aldehydes would then yield phenethylamines. In this example, a substituted nitrotoluene was condensed with DMF dimethylacetal, what gave a high yield of 2 enamines. Hydroformylation of styrenes can yield aryl acetaldehydes. In this example, hydroformylation in the presence of aniline led mainly to the phenethylamine and a small amount of 3-aryl propylamine. Let's check some potential side reactions. Base-catalyzed condensations or acylations of nitromethane can cause the formation of metazoic acid, as sketched here. This self-condensation of nitromethane is strongly exothermic and can lead to thermal runaways if conducted on a larger scale. Thus, an excess of nitromethane is usually used for condensations or acylations to compensate for the losses caused by this side reaction. Moreover, it is often safer to slowly dose nitromethane or the base as the last reagent to prevent the simultaneous buildup of high concentrations of nitromethane and strong bases. I showed you 3 examples of a copper-catalyzed benzylation of nitroalkanes at carbon. However, under alkaline conditions, nitroalkanes are usually benzylated at oxygen, as sketched here. In fact, 2-nitropropane is a convenient reagent for oxidizing benzylic electrophiles to benzaldehydes. As byproduct, oximes are formed. If benzaldehydes or aryl ketones are condensed with an excess of nitromethane, a Michael addition to the initially formed nitrostyrene might occur, as in this example. Aldol additions and condensations of nitroalkanes are reversible, and strong bases or nucleophiles can bring about CC bond cleavage. Oximes and hydroxylamines are formed as intermediates during the reduction of nitro groups. Occasionally, these may be obtained as byproducts, as in this example. Hydroxylamines are strong nucleophiles and can react with carboxylic esters, alkyl halides, and even nitriles if these were used as solvents. Nitroalkanes with alpha hydrogen may also be hydrolyzed to ketones in the so-called Neff reaction. As shown here, this can also occur during the reduction of nitrostyrenes. This is another example of Neff reaction, again under slightly acidic conditions. Neff reactions may be prevented by excluding water and alcohols from the reaction mixture. During the reduction of nitrostyrenes, many intermediates are formed that can react with each other. Here, for instance, a pyridine was formed in high yield. A higher dilution can sometimes suppress such oligomerizations. Despite the strength of CC bonds, cyano groups often behave like halides. For example, treating nitriles with sodium or other metals can cause reductive decyanation, as shown here. In this example, a tertiary nitrile was cleaved by heating with sodium hydride and lithium iodide. Decyanation of benzylic nitriles can even occur under oxidizing conditions, as shown here. All these fragmentations seem to proceed by radical intermediates and may be avoided by keeping the reaction temperature low and excluding any potential source of radicals. Here are some further references which you can also find in the description of this video. Under the Community tab of my channel there is a PDF version of the slides. The next video of this playlist is about the preparation of phenethylamines by aminomethylation of arenes or aryl halides. See you!